Okay, I think we're just about on time here, and so I'm going to pick up here again on chemical looping. You know, we talked about the how you get the oxygen into the fuel reactor and what are the limits on conversion there. One thing I didn't touch on was, well, what happens if you're not quite perfect about it? All right? Because you could imagine if you had iron that you reduced iron oxide that you reduced down to one of the reduced states, and there's carbonaceous fuel near it, you could imagine very easily making coke, carbon, right? You don't have to worry about that. You're going to see it in a minute, as long as you don't leave the oxygen carrier in there too long. But nothing's perfect, so you may actually have to worry about carbon being carried back out of the system. Sorry, I lost my pointer. Here we go. Carbon being carried back out of the system here. For example, if this was solid fuel coal and you didn't complete the conversion of all the coal and it comes through that loop seal and ends up going to the air reactor, well, what happens to that carbon in the air reactor? It makes carbon dioxide. All right? And if you do that enough, why did I spend all my time doing chemical looping, right? So you got to make sure you don't leave carbon, you know, on the carrier as it comes out of this process. All right, and so we're not going to get into equilibrium for yet another problem today, but here's equilibrium for carbon, you know, volume fraction of CO. This is just for carbon, CO2, CO. You can see right away there the ratio of the volume fraction of CO to CO2 plays a role, just as we saw here, plotted against temperature. And so, you know, this tells you where the carbon is forming at high values of CO, and, you know, you're going to want to avoid this particular region. Luckily, for most of these processes, we're going to run, you know, around 800 degrees centigrade, somewhere in this region, so you can have a lot of CO before you start making solid carbon, all right? But you do want to be aware of that, right? You don't want to make solid carbon and bump into that equilibrium line. It's a big headache when you do experiments, though. Like if you do fuel cells and you try to convert hydrocarbons to carbon monoxide, you heat the hydrocarbons up in an environment where there's not a lot of oxygen, you get a little bit of CO. You might be right down in this temperature range. You can see there's 0.1, 1 times 10 to the 2. So you get maybe 10 or 20% CO and you start forming carbon. And boy, it forms like that and it plugs everything up. So if you have to work in chemical looping or fuel conversion, you want to get familiar with that type of plot, because it'll tell you where am I going to have to worry about solid carbon forming, and the easiest way to get around it is drive that temperature up or consume some of that CO. All right, don't let it get too high or you get into solid carbon formation. Okay? So there's a last little bit there on equilibrium just to talk about carbon formation. And we'll get to a little bit later, if you put solid carbon on a metal oxide, you'll see this is like really fascinating. It might not even be a problem. But let's take a look now at some more details of the oxygen carrier itself. All right, so I just want to put some nomenclature together here for you. The conversion for a supported metal oxide carrier. Supported means you might put that metal oxide, for a whole bunch of reasons, on an inert support, like aluminum oxide, right? Because it's not going to enter into that reaction. You might want to put like copper or iron on that. And here I'm showing it in a fully reduced state. And you know, the way you define this conversion is the mass of the carrier minus the mass in the fully reduced state versus the fully oxidized minus the reduced state. So when you fully oxidize all that active material, the conversion is 1. When you fully reduce it, the conversion is 0. Make sense? Just puts it on a scale from 0 to 1, where 0 is, you know, fully reduced and 1 is fully oxidized. And that's the nomenclature you'll find in the literature. And in addition to that, you know, expression for conversion, you also, if you look through the literature, find this definition of the oxygen transport capacity. That's the difference between the oxide mass, the reduced mass, divided just by the oxygen mass. That's a property of the particular chemical reaction you're interested in, like iron to iron oxide, copper to copper oxide. It doesn't say anything about supported materials or anything like that. It's how much oxygen you can carry for a particular reaction, and then you correct that to account for any inert support with this quantity chi0. And so just a way to, you know, see that graphically, here's the mass of a carrier. 1 kilogram in the fully oxidized state would be right up here. All right, this, you know, B is the inert mass, A is the active mass fully oxidized, and then this quantity up in, then the C is the working oxygen capacity. That's how much you're swinging back and forth between these two states, which I showed here just to be realistic. You're not going to fully oxidize it over here. You're not going to fully reduce it. You might go 0.2 to 0.8. So that's the working capacity right up in there. And I deliberately put it on a graph here to give you a sense of how small the fraction of oxygen is, right? It is perhaps surprising the first time people think about chemical looping. If you look at like iron, the highest oxidation state, hematite dropping down to the next lower one, magnetite, it's only 3% change in the mass of that material. It's a very small amount of oxygen, so you have to move a lot of that material around. In fact, I think on the next slide we'll take a look at some different materials you might choose as an oxygen carrier. And here I'm plotting their capacity, that R naught, for some metal and oxide pairs. And this is the one I just mentioned a moment ago, iron hematite going to magnetite, about 3.4% oxygen by mass as you make that transition. Doesn't sound like a lot, so you realize you're going to have to circulate a lot of that material. But you have other options. You could take it all the way to FeO from Fe2O3. That's 10% oxygen. I really like copper going all the way, copper oxide going all the way to copper, 20% by mass oxygen. And then this is the one I mentioned in my talk earlier, not really a metal, but a sulfate to a sulfide. It's almost half the mass comes off as oxygen. So you got a lot of oxygen if you could use that sulfate sulfide transition. And by the way, this one's really inexpensive too, right? I mean, you just dig calcium carbonate out of the ground, you throw it in with the coal, and it will sulfate if you put the conditions the right way, and you get a carrier out of it. And it's so cheap, you'd probably throw it away after a couple cycles. It's not so cheap if you're going to use copper or some of these other ones. So you have this trade-off between the costs and how you might elect to, operate the system. So we'll get into that in more detail here in a second. So let's just think about, well, if I had to build one of these, let's try to be realistic about, well, how much material could I circulate from a practical standpoint? And so I'm going here, just use some experience from the petrochemical industry, fluidized catalytic cracking, or FCC. These are, commercial processes that already exist, and they take solids, and you put in the hydrocarbon that you're trying to process here with some steam, and it basically coats up on solid particles. They go flying up into here as you heat that stuff up. You strip off the lighter hydrocarbons, and then the coke, or the solid carbon, comes back down with the material along this leg, and you basically burn it off. All right, and so that's how you change the C to H ratio when you're doing hydrocarbon processing. And this is a known process. It's been around a long time, and people know how to do it. And they actually circulate significant quantities of solid around this loop that look something like the oxygen carriers I've been describing. So you say, well, if I'm going to do chemical looping, it's going to be a process very similar to that. I'm making the solid go around in a loop like that. We already know these guys circulate huge quantities of solid. Look at the amount there, 41 tons per minute. Wow, that's a lot of material going around that loop. But at least establishes a practical experience base if I was going to try and build an actual chemical looping device. Well, if you then want to go backward and think, well, then which oxygen carriers could I use and get them to circulate at that rate? And how big of a power plant could I conceivably make? So we're taking that circulation rate that I just described a moment ago and then calculate the thermal output that's possible for a chemical looping system for some of these different materials like copper oxide to copper or hematite to magnetite. And all you're doing, you're saying, I'm going to take that oxide and figure out how much oxygen I can get off of it and react it with fuel, and then that'll give me the heat release rate, and it'll tell me how much heat can I get out of that process. All right, so very straightforward calculation. And what I'm showing here then is the thermal output that you would get for that circulation rate of an oxygen carrier. And you start to look at some of the numbers, and it's really quite impressive here. That's megawatts on this scale. All right, and kind of a mid-size existing coal power plant is like around 500 megawatts right up in here. So if I was going to use this as a carrier, all right, this is telling me, I'd have to go circulate more than industrial experience exists if I was going to use that carrier. So it's starting to get pretty big. On the other hand, if I did this one, I'm way over that 500. All right, this one's not so good. All right, look at the copper one there. Wow, that's impressive. I didn't put the sulfate one on there because it's huge. All right, the point I'm trying to make clear, these numbers of thermal output, even for modest levels of conversion, not fully converting the thing, you start to get into the range where it's possible to make power plants of the size that we're familiar with without exceeding a circulation rate that's already common in industry. All right? So I looked at that slide and I thought, oh, it's like we can make these things. Yeah, we probably can. It's not out of the realm of experience. But there's a few more details. This is a first order estimate, and all I've done here is account for supplying oxygen, not the thermal balance. All right? So now we're going to go back to what we started with a little bit earlier and say, well, how exactly did we calculate the solid circulation rate here? Remember I said for these endothermic carriers, how do you get the heat over to the fuel reactor? It comes with the mass going over with it. All right, so let's see what that means in terms of an actual design. The oxygen carrier circulation rate is determined by the oxygen that needs to go over for that particular fuel flow rate. But if you have an endothermic carrier, you've got to get the heat over there as well. All right, so you have to actually do a calculation and account for those two things. And it turns out, as you'll see in a moment here, the circulation rate sometimes, in fact most oftenly, is determined by the thermal balance, not the supply of oxygen. So let's take a look at what that means. Whoop, wrong way. Okay, so let's get into a little bit of analysis. So I've shown, I can't see my own slide here, let me walk here. I'm showing in the background, the same schematic I've shown before for a chemical looper, and I'm trying to isolate the air reactor, that's the blue, from the fuel reactor. And then I show two different circulation rates, A and B. Well, of course, there's only one actual circulation rate, but I'm showing two to emphasize what I just said in the last slide. You've got to get oxygen over to react the fuel, but if it's an endothermic carrier, you've got to bring the heat over with it. All right, so A and B. So A, supply enough oxygen. B, bring over the heat. Well, which number is bigger? A enough to give the oxygen or B enough to give the heat? Well, let's take a look on the next slide here. I just calculated that out. You can do it yourself, just looking up the thermodynamics of those properties. And there they are plotted up, the A and the B quantities, the two different circulation rates. And I did this, and this is all a reasonable estimate. I'm assuming here you're willing to allow the fuel reactor temperature to drop about 50 degrees centigrade. So in other words, the carrier might come in at 800 degrees centigrade. It drops out of the bottom at 750. You don't want to get too cold, so you start running into carbon formation, or you can't actually then manage the loop around the air side as well. So here's what you get for different carriers. So that's the iron going to its next lowest state. That's hematite to magnetite. And then it goes down to wustite, and then there's pure iron down there. All right, and I'm here calculating the circulation rate to supply the oxygen right here. This is all done on the basis of a megawatt thermal output, just to be convenient. So I'm plotting it up. Kilograms per second of oxygen. I'm going to flow around that loop to supply a megawatt thermal, fuel flow of a megawatt thermal. If you want to get into the details, this is for a natural gas or a methane analysis. And you can see as I increase the amount of oxygen that's coming off the carrier, right, I'm going from this oxidation state down, down. I don't need to circulate as much to supply oxygen. Did that make sense? Iron has 3 oxidation states. Every one of them gives off more oxygen. So you need to circulate less as you go further down here, right? But this is an endothermic carrier, all right? So when it's coming over, the more oxygen I'm popping off, the more heat it takes, and the more I've got to circulate to provide that heat. And look what happens. The circulation rate goes up, and it goes up pretty substantially, right? So if you want to reduce that material down further, you think, well, I'll just take, I don't want to circulate as much. I'm going to just reduce it all the way down. Look at how much, oh, well, you can't do that. You've still got to bring that heat over, and so you end up, the design is controlled by how much heat has to come over with that material. That's what you're seeing right here. And it's really interesting to look at the actual ratio of B to A. It's 22 times more in terms of the circ rate, just to bring the heat over it than it is to supply the oxygen that you need. All right? The actual quantities, the circ rates, they change by about a factor of 2 down here. It's interesting if you look down here at copper. Remember, copper is the unusual one. Remember way back I said it's exothermic. So you don't have any constraint here in terms of circulation rate for the thermal balance. You just supply enough to give you the oxygen. So it's kind of in a unique category. And you know, it's interesting because then when you actually run the thing, you have a lot of freedom in terms of how you circulate the material, because I don't have to worry about the reaction, the fuel reactor getting quenched. Does that make sense? It's a really interesting material. And then you could think, well, maybe even better if I just made a neutral carrier. I don't have to worry about it at all, because here I'd have to actually take some heat out, you know, with pure copper. So we'll talk about neutral carriers a little bit later. But this is the point. By the way, calcium sulfate to sulfide, remember I said lots and lots of oxygen, about half of it. So you don't need to circulate a lot to supply oxygen, but by golly, you got to circulate a lot to bring the energy over that you need to drive the reaction. All right? So when you think about how you're circulating those solids, two things to remember. Got to bring the heat over, got to bring the oxygen over. If I have an exothermic carrier, I don't have to worry about bringing heat over there. So that's just a basic balance in terms of, you know, how would I design these reactors. But then you got to worry about kinetics. Does this sound like a combustion class, right? You start with thermodynamics, you start going through mass balances, now we're at kinetics. There's all the same stuff that you do in any other combustion design. It's just a little bit different because it's heterogeneous. So kinetics rates obviously determine the reactor size, and you just want to put together a quick example here, how that works. How would you actually put together the reactor? And I'm looking here at an air reactor. Well, this is typically done in a fluid bed, and we'll spend time talking about fluid beds in just a few moments. But these fluid beds, they behave almost like a well-stirred reactor for the particles that exist in the bed. And so you can treat it like a well-stirred reactor with a given volume, a given set of inputs, given set of outputs. If you do that, you can write the kinds of balance equations that you see. We'll get to that in a second. But you need to put in a kinetic rate. So this is a little bit different than most probably the combustion work that you've been doing. Where do you get the rates from? All right, because it's a heterogeneous rate. How do you measure that? First step is probably in a thermogravimetric or TGA analyzer, right? You just load the material up onto a pan that you can take a measurement of the weight of that, and then you actually measure the conversion just by watching the change in time of the mass that's sitting on the pan, right? Because if you put the metal in there and you put oxygen over at temperature, its weight will go up, right? And you can actually then measure how it is oxidizing from that TGA profile. And so here's an example of a TGA profile, just as I described it, where you're watching the red here is the mass. And what you're doing first is putting in this case, it was methane fuel, and the weight drops because you're pulling the oxygen off, wait a few moments, purge it out, then put oxygen in, and it goes back up. And you can do that cycle again and again and again, and you then are able to actually calculate the kinetics of the process after you run that data through a correlation. Here it is in terms of the conversion, and you can see you can get very nice prediction of the conversion rates just by correlating the data with this particular approach. Says it's a nucleation process that drives the kinetics. So that's how you get the kinetics for the process. And I thought it'd be fun. I actually used this slide last time. I'm going to do it again because I just wanted it gives you a real graphic way to see what actually happens. And besides, it was my first major movie that I ever made. I was so proud. I did this on my own little computer. If I could just play it now. There it goes. Okay. Now if we can stop it. I even put that title in there. I was so proud of myself. All right, so what you're going to see is copper oxide reduction back and forth, because I want to give you a sense of how fast does this process actually occur. All right, so what you'll see is two wires and a propane torch. All right, so now we'll see if we got any communication with you today. What's the partial pressure of oxygen, give or take, inside that kind of inner cone of a propane torch? The partial pressure of oxygen, is it 1/10 of an atmosphere? The partial pressure of oxygen inside that, not right at the very leading edge. There's two cones in there. When you run it a little bit rich, partial pressure of oxygen, is it 1/10 of an atmosphere? Please say no. No. All right, it's not. That's atmospheric pressure in the room, right? That propane torch, what you've done is you do a partial combustion. It's a partially premixed flame, right? So there's a low partial pressure of oxygen because there's a lot of CO and hydrogen, you're still burning up in that outer region of the flame. So you go back to those Ellingham diagrams, that part of the flame is where the oxygen partial pressure is low, and it will pull the oxygen off the metal, and you'll be able to see it quite graphically here as I play this. So let's go ahead and play it here. So there's my propane torch, and there's just 2 copper wires. I just put them on a piece of wood there. You can see them sticking off the end and the end of my torch, and then we just do a bit of a close-up. So there's the torch, and you can see that inner blue region. Now this is easy to see because it glows, and copper itself is kind of shiny, like a shiny penny, and the oxide is darker. So watch what happens right as I move back and forth. Can you see the copper going back and forth to copper oxide? You can see the shiny part there, and as soon as I get that out into the air, it gets dark again. You don't see that reflection because it's going to copper oxide. At least that's what I'm pretty sure is happening there, right? It all makes sense because you can look it up on an Ellingham diagram, and it has to happen that way. All right, so you can see as I'm playing the torch back and forth on there, you can see that the copper oxide is outside of the torch where the air is reacting with it, and there's a reducing environment on the inside of the torch where you can see it's going to copper. So at least right on the surface, I'm taking it back and forth from copper to copper oxide. And it's just a very fun way to see it, and it gave me a sense visually, you know, that the process really does happen as we've described it, you know, this afternoon. And it's funny because I noticed that while I was doing, you know, some work with copper in my basement. I thought, wow, this would be great to, you know, get an image of that. Okay, back to slides here. All right, so having said these kinetics are pretty fast, and we've shown, you know, that they are, you can actually do this mathematically. You can put together a stirred reactor equation. You can write an efficiency expression. If you do stirred reactors, you probably recognize this. You know, X minus the initial conversion going into the reactor. And you can plot this efficiency, the extent of conversion on one axis, and the internal temperature of the reactor. Obviously, if I have the conversion running along this axis, and that conversion is liberating heat, then the temperature in the reactor will go up linearly as I convert more of the material. The straight line ought to make sense to you from that standpoint, right? Just saying, as I convert more of this, I'm releasing more heat as I move along that axis. This is the plot of kinetics, all right? The efficiency, the amount of conversion, where you actually have the kinetics in there. And what it says is, if I want to get to very high conversion rates, I have to have, I have to have a high enough temperature to drive the kinetics up with a fixed, residence time to get up to that level. This is standard stirred reactor theory, and you just, where those two lines meet, it tells you where the thing's going to operate, right? And so interesting, I actually did this for the cases we're studying. There's no light-off behavior here, all right? It just says it's going to run at that condition. That's not necessarily true for all cases. If you actually, change the flow rates, you go, that's the slope of this line, you actually find there's two solutions. So you could actually have a light-off behavior in the system, which really worried me, because when you're actually running one of these things, right, you don't want to have it suddenly jump to an ignited state or extinguish it, right? That's what happens when you have blowout in a conventional combustor. All I'm trying to show on these slides is it has the potential to have the same type of dynamics that you get in any combustion system, right? You have light-off and extinction. And so you have to plan for both of those events, and that's how you put the kinetics in there. So I spent a moment talking about kinetics, and I'm going to share this next slide just because this isn't obvious if you don't work in heterogeneous reactions like this, and it's easy to overlook. You think, well, how quick do the reactions actually need to occur to get them to react in a given box? So, like most things, it depends on some different parameters. So what I'm showing here is a reaction where you're going from, I'm showing it blue then to red, okay? So if you have the mass flow of the active species, all right, so that might be the oxygen carrier that's going in there. You have a certain active mass that's sitting in the bed. It has a particular residence time, which is the mass divided by the flow rate. And then that has some heat release per unit mass going on in that bed. You just take the ratio of those, and you have the thermal output per unit volume. And then you take the density of the active mass. I'm talking about the density in the reactor, right? It's not the density of the discrete particle, but the density, how much you've got in that volume. All right, multiply top and bottom. And there you go. The thermal output per unit volume makes sense. The amount of active material per unit volume, the heat of reaction, and the residence time that it sits in that particular reactor. So if you just make a simple estimate here and say I want my conversion, to be complete, the rate constant dxdt, assume it's just constant, so then T times the rate is the amount of conversion. I assume I want it to be fully converted, so combine that and that down there, and this should make sense. The thermal output per unit volume inside of that box is the active mass, the heat of the reaction, and then the rate that it's being converted. That makes sense. I think there's just physically multiply it together and you can see that. So can you build a reactor for chemical looping of a size that's reasonable with the kinetics that we understand? And the answer is yeah. And you can check that yourself. I went in and just did it for a fluid bed combustor, not a chemical looping combustor. So I want to see, will this thing look a lot different than what we already know how to build today? So you can go look up in a book what's the active amount of material for coal in a fluid bed reactor. You can look up the bed density. It's 2% of that is going to be a coal. And there's the bed density in a fluid bed reactor. Residence time for coal in those systems. You can look up that reference. I've got it noted there. The heat of reaction. It leads to a volumetric heat release rate for bubbling bed combustors of about that value, 3.8, not quite 4 megajoules per cubic meter. Well, it turns out if you put in chemical looping oxygen carriers, you can get to those levels too. You have to know the kinetics. We've measured them in the lab. My point in this slide, two things. One is it's reasonable to think you could build one of these devices at a scale that's comparable to what we know how to do today. Second thing, and this is the part that gets sometimes, it's hard to appreciate this until you work on this for a little bit. You can actually adjust the active density that's in the bed, right? Again, I said it's not the density of the particle, it's how much is in that bed volume. So you could imagine diluting the bed out, right? Put sand in it. That's what you do in a fluid bed, right? Fluid bed combustors today, only about 2% of the bed is the coal. The rest is just sand going around in there to keep the temperature nice and even, all right? Well, if I'm worried about the kinetics in my chemical looping system, if they're not fast enough, guess what? I don't need 2% of them then. I can put in a lot of them and I can really jack up the reaction rate because I can put more material in there. And it isn't always appreciated. People think, well, how can you do this chemical looping when you've got to react this solid metal? Isn't it too slow? Well, it might be, but I'm trying to tell you it probably isn't and doesn't have to be because I can load it up with a lot of that material. So even if the individual particles are not reacting that quickly, I can put a lot more of them in there. Can adjust the active density, all right? So it's a little bit different than probably most combustion problems you've worked on, and it turns out to be very valuable understanding as you look at the designs we'll see later. My main point, you can adjust the active density. Let's take a look at solid fuel combustion before we jump into actually how you design a reactor. And this is a very interesting story because it just shows how wrong you could be. This is an experiment we did now a long time ago on a TGA pan, and this is one of those thermogravimetric analyzer profiles. So this is the weight of coal that's sitting on that pan in a laboratory environment. And this is the time running along this axis. The blue line here shows the temperature. So you load the coal onto that pan and then you start ramping the temperature up over a period of minutes. And when you put that coal in an environment, the gaseous environment here is nitrogen, you start heating it up, the temperature goes up to, in this case, about 1,000 centigrade. As you heat it up, the mass of material from that coal starts to drop, and it gets to a certain level and then just plateaus because what you've done is heated it up and driven all the volatiles off the coal, and so the pan is just left with all the solid carbon, all right? So then if you put air or oxygen in at that point, the mass drops even further because you burn the carbon out of there, and so then you get down to the empty pan and you have just the ash that's left from the coal. So that's how it works when you put coal on a pan and you heat it up. So he said, well, let's put copper oxide, an oxygen carrier, on that pan, mix it up with the coal, put enough copper oxide in there that I could consume all that carbon, and then heat it up in nitrogen again. So there's no gaseous oxygen. I'm now heating that up. And look at what happens to the mass on the pan. golly, it goes way down all in one step. Plateaus way down here. Significant reduction. In fact, all the carbon's gone. You know, and to prove that, then when you put the oxygen in, look what happens. The weight goes back up. How come? The copper's picking up oxygen again, so the weight goes back up. So what you're seeing is you really did actually, you know, get rid of all the carbon. You burn it off with the oxygen from the copper oxide, just like we showed on the movie, right? That's where the oxygen came from, out of there. And then when you put the oxygen back in, you reoxidize the copper. So it is chemical looping on a little pan. Just, you know, you're doing it back and forth here. Well, that's all fine, and we expected that to happen, but the thing we didn't expect was it went way too fast. And we went round and round in circles about rates on this, and I couldn't believe that it was going as quickly as it was. And I kept trying to come up with this model for it and kept looking at like how the gas would go back and forth. I probably spent 6 months doing a model of reaction between a plane of carbon and a plane of copper oxide, and I was getting all these rates, and it didn't work. And it was a lot of fun because my colleague Ranjani Sirwarden and I, we were going back and forth like, why doesn't this work? So let's take a look at why we were able to get such high reaction rates, because it's an interesting story and it's practically very valuable to know about. If you want to react a solid carbon like coal, you know, in chemical looping in nitrogen, here's the case where nitrogen, we're taking the coal, we're heating it up, you get pyrolysis, all right? Then let's treat those pyrolysis products as CO and hydrogen. Those could react then with the copper oxide, the gas phase reacting with copper oxide, reducing it down to copper, CO2, and water. That's what I was trying to develop a model for, and I could not explain the rates that we were observing in the lab. You could also gasify the carbon that's there with CO2 to give you CO, and then that would react over here with the copper oxide. That is a credible route to actually, you know, have coal react with copper oxide. Couldn't get it to work right when I tried to model it. If you have CO2 as the environment, well, then you can gasify the carbon with the CO2. You get the CO, and again, you have this gas phase reaction with the copper oxide. And again, that's a credible mechanism for reaction between these species. There's also a mechanism which you'll hear referred to in the literature as CLOU, C-L-O-U, chemical looping oxygen uncoupled. And the way that works is if you heat up copper, it will actually decompose, when you heat up copper oxide, it'll decompose and release oxygen if you get the temperature high enough. So that's another route to chemical looping. And then, of course, the coal would react directly with the oxygen. But there's one mechanism that, at least when we were doing this work, we didn't really think this was going to go fast enough, and that is you just get the carbon reacting directly with the other solid metal oxide, which just seems like it should be really slow. I kept saying it can't be that mechanism. But we did some work and found out we were wrong. And here's the proof of that. And you can go in and look through the papers on this point. So we said, if I had copper oxide, all right, remember we went through the Ellingham diagrams? At 500 degrees C, the partial pressure of oxygen is like 10 to the minus 9. Not much oxygen comes off of copper oxide when you heat it to 500 C. Very low partial pressure. We went into the lab and we took the same carbon on the TGA pan that we were going to use with the oxygen carrier. We set the oxygen partial pressure at 10 to the minus 2, much higher than that. And man, it didn't barely react at all. I mean, it wasn't moving anywhere, wasn't going anywhere. Just sitting on the pan with, 1% of oxygen, wasn't reacting hardly at all. Well, if I have copper oxide sitting in there, which I know has this equilibrium partial pressure of 10 to the minus 9, then how could this go faster than this? It can't, right? How would it get to the oxygen? Well, right away you think about that and you realize then the only possible explanation is these things are reacting directly through the solid phase. That's the only explanation you can come up with. Does that make sense? I mean, you couldn't come up with any other explanation for it at all. So we said, well, let's do the obvious thing here. Let's take that bed of material. Remember I said in chemical looping, you can change the active density. And that's what we did. We took that coal, we took that copper oxide. Did I get this one right? Oh, I skipped ahead one. First of all, before diluting that, we just looked at different particle sizes of coal. So you'd change the contact area between the coal and the copper oxide. All right, so you look at small particles. Here's the temperature profile in the TGA coming up. You get in here and you start to see significant reactions between the two measured on the TGA pan, you know, and you get up to here, it's really a fairly rapid reaction rate. That's the conversion per minute. And then if you start to make the particles bigger so they don't contact as much, you get, you know, the temperature that you need for the same reaction rate moves out further. And then if you make even larger particles, it moves out further still, and the rate is slower. So I'm thinking, wow, the particle sizes are playing a role. And this is where I got ahead of myself. You could look at the same issue by diluting the active density, right? We just literally put silica in there and mixed it in with the carrier. So you're making the active contact, or the active amount of material, less. And lo and behold, same behavior. This was with pure carbon, copper oxide mixed together. You heat the thing up, you get good reactions at relatively low temperature. As you start to dilute it, 1 to 5, that temperature goes up further. As you start to separate those particles even further, it moves to yet a higher temperature. And you know, the point here is there's really no explanation to come up with other than these particles touch each other and they react directly through the solid phase. So am I saying that to build a chemical looper, I want to grind up all my carrier and my carbon until they're really small and in intimate contact? Well, that's one conclusion you could draw. It would help. I don't know if you'd want to design a practical system to do that, but it's an important understanding to have. Why? Because if I'm going to use this with coal, the first thing that's going to happen, those volatiles are going to come off in an environment where there's low gas phase, oxygen partial pressure, and you're going to deposit them all over the carrier, right? All that tar and stuff that's in coal is going to get on the carrier. And you know how it's going to get oxidized? Solid-solid reaction, quickly. Well, that's actually a good thing, right? And it's one we just stumbled into while we were working on this. And it's very valuable to know about, both from the standpoint of getting rid of carbon that might form on that carrier. As long as there's oxygen in there, it'll react. And also because it tells you the particle sizes could matter for heterogeneous reaction. That's useful for other things too, by the way. You know, you could make similar arguments for developing propellants. You know, one of the things that occurred to us, if we first started to understand this, I thought, oh, you know what we'll do? Make a green propellant. We'll take carbon, we'll mix it with, I don't know, pick something, copper oxide, stick them together. If you light one end, they'll just burn automatically, right? Solid, solid. There's only one problem with that. The material that's left is copper, which is pretty heavy, and if you're trying to make propellants, it's probably not what you want to do, right? But maybe one of you can think up some great invention that'll take just that solid product and just to create heat, you know, would work. And I've actually seen papers where people are starting to look at things like that. I don't know how you would use it, but anyway, it's an interesting idea. All right, move on now to, I've taken you through, you know, here's some of the basic reactions that are involved, the thermodynamic limits of conversion, the kinetic rates, and how do you at least get a sense of what are the flow rates I've got to use in the system. How do you actually go in and design a reactor to use chemical looping? If you can figure that out, would you come see me at the end? Because I need help. We're struggling with this, as everyone else is around the world who's looking at this. So I'm going to outline to you what the issues are and tell you the different ways people are approaching reactor design. To understand reactor design, you need to understand fluidization, because you've got these solid particles. So you're going to get a crash course in fluidization, 415, did we say? Oh, okay. So I got, boy, it'll be a really crash course. All right. So we're going to go through fluidization. It's widely used in the chemical industry for FCC, I've mentioned, catalytic reactors. If you work in alternative fuels like biomass, then you have to start thinking about this area. So maybe if there are alternative fuels people or gasification people, all right, this is bread and butter for low temperature gasification, and it's obviously important for chemical looping. So there's a list of the topics we're just going to fly through today, you know, to give you an introduction to fluidization. If you work in this area, I've listed, I think, two of probably the best references I've found. The one is widely known to everybody and anybody, the Cooney and Levenspiel. Get a copy of that if you're going to work in fluidization. The one on the top, I find that text to actually have the best practical information. It gives you all the numbers of like what are the ranges of parameters, you know, for fluidization. So there's some really good references there. So here's a physical description of fluidization if you've not worked in this area. You know, granular material, it won't typically flow like a fluid. If you have, you know, a reactor volume just with like a mesh at the bottom there and you dump a bunch of sand in it, it'll form a pile. All right, that's what I'm showing right here. Now if you add air or a gas to the bottom of that, you'll start to fluidize it and the volume will grow a little bit and it will look just like a fluid. If you tip, you know, the vessel over as I'm showing here, it will level that surface just like, you know, a bottle of water. Where's my bottle of water that's not full, right? That's what a fluid does. I tip it in an angle and it takes a level surface. Well, solids will do that too as long as you put that fluidizing gas in there. And it'll flow out of a hole just like if I punch a hole in the side of a water bottle. As long as it's fluidized, it'll be able to equalize levels if I put a divider plate in here. When there's no gas, you know, you'll be able to pile stuff in here and it'll be frictionally jammed through here. Now when you fluidize it, those two surfaces will level out. And interesting enough, you know, you don't think of this initially, but that also means that light objects will float in fluidized environments. So I'm showing a fluidized bed there. If I had a heavy weight and threw it in, it would sink to the bottom. If I started with a, you know, inflatable rubber ducky in here and fluidize it, it'll pop out of the top. And go on the internet and type in fluidization movies and you will laugh your head off because of copyright. I couldn't show you some here today, but you know, some of them I found, for example, you know, they were using fluidization as a secret trap in front of a doorway, right? Where you can walk on a bed of sand, right? If it's filled like a dumpster below you to 10 or 20 feet, and then somebody puts the fluidization air in, guess what happens? Down you go. And there's an internet video clip on that, so now you'll all go try that. You guys are young, you'll be doing it on you. You won't even listen to me anymore. Maybe at the break, we'll pull one up, okay? So light things float, heavy things will sink. Just so you have some familiarity with the nomenclature, the void fraction, it's probably the most common parameter when you speak of fluidization. It's how much volume of gas relative to the total volume that's sitting in that region. And it has surprisingly wide range of values in practical systems. So in a packed bed, meaning just like a bed of sand, epsilon equal a half means it's half empty space and half solids, right? So when you put in a bubbling bed, like in a combustor, you might start at a half and then it'll drive up to maybe, you know, to 85% of that is actually the gas volume. And interesting, when you get up to like circulating bed combustors, circulating fluidized bed combustors or chemical loopers, the void fractions there are remarkably large. All right, so it's very dilute flow at that point. But that solid particle is 1,000 times more massive than the gas that's around it. Right? So the actual mass flows of gas or solids are actually very large, even though the void fraction is close to 1, meaning it's mostly empty space. All right? So there's some typical ranges of those parameters. Oh, wait a minute, I wanted to mention on the bottom there. And one of the most helpful things you can remember from today's lecture is, well, how much pressure drop exists across a fluidized bed? Well, it is even hard to figure out, right? You have to lift the bed and support it by the airflow. And so it's just a very easy calculation. The pressure drop has got to equal the mass of the bed material. It's that simple. And you know, you can look through the equation there, but it's just a very simple thing to remember, and you'll understand like how you get the pressure drop. So there's parameters that are used for people who work in fluidization that you'll hear a lot of. The minimum fluidization velocity. It's the minimum amount of the superficial velocity. By the way, superficial velocity, just the bulk gas flow. Imagine that all the particles weren't there. Right? So that's the velocity where you just fluidize the bed, and the weight of that bed balances the pressure drop. And typically with most materials, you actually just go measure it. You can't predict it. Can't look it up in a chart. There's enough differences in morphology. You need to measure it for new material. And there's also minimum bubbling velocity. That's the velocity, the superficial velocity, where you start to see discrete bubbles form in the bed. All right? And that can actually be greater than the minimum fluidization, and you'd have sort of smooth fluidization. You can imagine you're putting that gas in, the bed volume goes up, you start to flow through it, and you add a little bit more and add a little more, and then finally you start to get these discrete bubbles. Now there are certain materials, type Bs, that it won't happen that way. You'll just start going right to bubbles, so we'll get to that a little bit later here. Then you also have to think about the particle terminal velocity, right, which I think you know what that is, right? If you exceed that, then the particle is just going to rise up with the gas flow. Now, keep in mind that the actual flow through the system is not uniform. As you increase the velocity, there's going to be a lot of non-uniformities. So you can actually drive above that bulk superficial velocity, above the terminal velocity, and you get streamers in there where the velocity is lower. You won't just push them all out at once. You will if you get the velocity high enough. You'll lift the whole bed out and carry it out. So those are the kind of, velocity parameters. And then there are different regimes of fluidization, which I've sort of taken you through here just schematically. Very smooth. You get into the bubbling region. Then you get a region where you can't see discrete bubbles anymore. Fast. You've got those streamers moving up through the top. And then finally, you just lift the whole thing out. It's pneumatically conveyed out of there. All right, so different regimes for this. And I'm just about at the break here. So how does this fit with chemical looping? Well, here's a reactor that we actually run in our laboratory. We'll go into it in a little bit detail later here. This is a real design and it's pretty much shown to scale. This is the fuel reactor. The colors represent that void fraction. So this is the dilute void fraction, epsilon up in here. It's very dilute. There's not many particles up in that region. This is actually then a bubbling bed where the actual fuel reacts with the oxygen carrier. The carrier then drops down across the bottom here, and then you add a fluidizing gas, the air in this case, that produces the oxidation of the carrier. That's carried up this leg, and it arrives in this cyclone. It's separated out. It goes through this loop seal. I'll cover that in just a second. Then drops back through the fuel reactor. So that's the loop for chemical looping. And I've pretty well described how it works. You run this part of the reactor with a velocity above the terminal velocity. So eventually where you neck down, you will carry that stuff up and out, separate in the cyclone. It'll drop back down. Here we've got to keep the velocity above minimum fluidization, but below that terminal velocity. So I'm trying not to carry particles up in this part of the reactor. So that's how it works. So let's see if this makes some sense here right before the break. Where's the pressure highest around this loop? Stop and think about that for a minute. Where is the pressure highest as you go around that loop? Somebody's pointing. Anybody volunteering? It doesn't matter if you're wrong. Don't feel bad. I'm wrong about most things. So right there, right? Because all those solids are sitting above it, right? It's right at that corner. That's the highest point. And so your design is really constrained by here, and what you have to do then is carry this up high enough to create a big enough bed of solids to control the circulation rate around that process. And the way you do that, control that circ rate, is by designing to let the solids flow go at a controlled rate along this leg. And how do you do that? Well, that's that job of the L valve. These things look so simple, but man, they are really, really hard to get to operate. This is that bottom leg just shown really large. You have the solids coming down. This is the highest pressure point, so the material's trying to go that way. If you don't add any fluidization gas, what happens? Stops dead when you don't fluidize it, right? Because solids don't flow like a fluid. So actually, to control the flow rate, you just control how much fluidization gas you put in that part, and that controls how much is going around that loop. If you don't put any, it will stop. By the way, if you do this in the lab and you stop it, well, just don't do that. We can talk later why you don't want to do that, all right? And then loop seal, all right? This was shown on that diagram. This is just handy to be aware of. You have the flow coming down this way. There's a bed of material. Think of it as like a liquid, in that region. It just fills up to this point and then spills over. So now whatever's going down here is isolated from whatever is up in here, which is how we keep the CO2 separate from the airstream. That loop seal, got to have one of those. All right, they too follow a design for fluidization. So I'm just about done before the break here, and we won't have a lot of time to go into fluidization today. But if you get into this area, you will need to know that particles affect the fluidization as well. Right? It's not just the design of the reactor, but the type of the particle, and the classifications are shown on the diagram, A, B, C, and D. If you have a particle in the category of Goddard type A, life is just wonderful. They flow almost like water. You'd think they were a real fluid. B is not quite as easy because you tend to get bubbles. C, don't even go there. this is just sitting in a vial. You see what's right there? Right in here? So if that's the middle of your reactor, good luck, because it's just going to jam up, it'll stop, and there'll be a big hole in the bed, and it's just very hard to fluidize. D is like jelly beans, trying to get them to flow. It's done, but not without a lot of effort. So you start to see designing one of these is very, very complicated because the sizes and the densities are controlled by what you want in terms of kinetics. But I've still got to fluidize it. That's why I made the comment earlier. It's like, if you can figure out how to design one of these, please come see me, because you're trading off all these different parameters. I think we better take a break. We'll come back and have a discussion a little bit about gas-solid reactors.